Hi class, this is number 7 on 8.2. So they say we want to obtain a sample to estimate a population mean. Based on previous evidence, researchers believe that the population standard deviation is approximately 65.8. We would like to be 90% confident that the estimate is within 2.5 of the true population mean. How large of a sample size is required? So whenever they ask for how large the sample size, it's just a formula that we're going to be having to plug into. We're just going to plug our values in and we're going to get our answer and then we're going to be done. Okay. So here's our formula to find the sample. This is the n, the number of the sample that's the number we're looking for. This is little s, is standard deviation, which they give us in the problem. And then this z alpha over 2, that's kind of a little complicated and we have to do a little bit of work to get what that number actually is, but we'll do that. But the e is the error, that's the 2.5. And this 90% is going to be something that we're going to talk, that's the z, that's tied into this z alpha over 2 thing. Okay, so first of all, before I have the e, I have the s, I can plug those in, but I don't have right now the z alpha over 2. So let me just talk about what z alpha means. Z sub alpha means this means that this is the z-score such that there's alpha area under the curve to the right. So it's a z-score, and we don't know what that z-score is yet, but it's a z-score such that there's alpha under the curve to the right. And so this type of problem, if I want to know, if I'm looking for the value along the horizontal axis and I know the area under the curve, then this was an inverse norm type of problem. Because most problems, they give you the value along the x-axis and we're looking for the area under the curve or the probability. So this is the opposite of that. So there's an inverse norm problem. So to find z alpha, what we do is we do inverse norm. And because whenever we use the inverse norm function, it has to be the area under the curve to the left. And this particular notation always gives you the area under the curve to the right. So you have to do one, so it's this area is the area that you need to input. It's giving you the black area, but you need to input the blue area, the area under the curve to the left. So to find that area to the left of our our desired z-score, you have to do 1 minus alpha, and that's because all of the area under this curve is one whole. So if the area under the curve to the right was alpha, the area under the curve to the left is 1 minus alpha. So it's 1 minus alpha. That's what we need to put, and it's that's what we need to put in parentheses here. And then you have to put the 0 and 1 because of the z-score, the mean of the z-score is 0 and the standard deviation is 1. So this is the formula for finding this z sub alpha. So actually, in our problem, we want to find a z alpha over 2. So if you just rewrite this equation and you replace the alpha with alpha over 2, then you can get the same kind of equation here. So they're saying there's alpha over 2 to the right, so there's 1 minus alpha over 2 to the left. And this is going to calculate for you this score that you need to plug in place of z alpha over 2, because z alpha over 2 is one variable. You know, it's one placeholder that we're going to put one number in for that. Okay. Now, one more thing before we actually calculate that is what is the alpha? What is the alpha? That's a question. So what I think of as alpha is alpha is what we're not confident. So if we're 90% confident, then how much are we unconfident, not confident? It's, so you do 100 to find alpha. Alpha equals 100% minus, and actually it has to be written as a decimal, but it's 100% minus our confidence level, okay? So that in this situation, it would be 100% minus 90%. And so our alpha would be 10%, but we always have to write it as a decimal when we plug it in. So it would be 0.1. So 0.1 over 2. So it's going to be the inverse norm of 1 minus 0.1 over 2. And that is, I do actually kind of have to divide that probably before I plug that in. But let's see how our calculator does it. Maybe we don't. But it literally is 0.1 divided by 2, which would be 0.05, or this point. So let's just see, maybe I can get away with it. I don't have to actually do that. So let's see, here's my class calc. I'm going to do inverse norm. And wait, inverse norm. Okay, so I first have to put the norm, so it's 0 is the mean and 1 is the standard deviation. And then now I have to put in parentheses, and then I have to do the inverse norm. That's how we do it on here. And now I have to put in this 1 minus, and I'm just going to see if it'll do it. I'm going to put it in parentheses to make sure it knows 0.1 divided by, and I've used the backslash, by 2 in parentheses. I don't know if it's going to like that for, I don't know. I might have to calculate what that is. Oh, yep. And it gives me the answer. It is 1.645 or 1.6448. So I might want to keep that, and so that is my answer right there. See, just in case you there may be some mistakes here, so you might want to do this beforehand. 0.1 divided by 2, that's 0.5, and just plug in 0.5 right here, because in order to not to make, in order just not to make mistakes. But this is our answer that we want, the 1.64585. I probably want to keep that really accurate to at least maybe 6 decimal places or so when we actually plug this in. So you write it down. Okay, so it is 1.64485. And I'll just keep one more decimal place, which would be, it would round to 4. All right. So now I might even be able to keep that actually in my calculator And then I could even just go and start calculating the next thing. So I could say, okay, well, now I plug in for this Z alpha over 2, for that whole thing, I'm plugging in this answer. So the next thing would be to multiply by the S. Which would be this 65.8. And then all divided by the E, that the E is the error, how far off you want to be, the 2.5, and then we would have to square all this. So I might keep this 1.645 in my calculator so I have all the decimals accuracy. Then I'm going to times by 65.8 and then divide by 2.5, and then I'm going to square my final answer. And then I'm going to round whatever answer I get up, always up. This is not traditional rounding, it's always up. So let's put that in. So I'm going to say times 65.8. Okay, I don't think it liked that. Okay, I think I have to re-enter everything. It just wants to do that. Okay. So I'm going to re-enter the, and I might even put in parentheses. I'm going to put 1.64485. Sorry about that. 53627. Okay, so I kept all those 644853627, and then I'm going to times by this 65.8, and then I'm going to, and I'm going to even do this, and I even like put an extra parenthesis in here, and then divide all that by the 2.5. And then now I'm going to even see if I can put a square on all that. Maybe if I highlight it, I'm not quite sure how I would do that, but let's see. Usually you can just do a little shift 6 and then to the second power. Okay, so I just did shift 6 and I did the second power. So I got this answer of 1874.24. There's 1,874.24 people. That's the number of people I need to sample. So it's 1874.24 people. And so that's my answer right here. And now what we have to always remember to do, this is the minimum amount of people that I need to sample. So if I sample anything more than that, that's fine, but this is just the minimum. So the best thing that we always have to do is round this number up and say, okay, well, if the minimum is 1,874 and a part of a person, then the actual minimum is rounding that one up, because we can't do part of a person. And so we do 1875 is our answer. Okay. Because there's no problems with sampling too many people. The too many people is great. The bigger the sample, the better. And in fact, we have to have the whole population, and that's really the best. We don't even need any more statistics anymore. We just do the whole population. So always rounding up here. Okay. All right. Let's double check our answer. And I don't know where this answer is. And maybe I did not. Sometimes I keep them and sometimes I don't. Okay, here's the problem. Okay. So, yep, 1875. Yep, that's what they wanted. It's exactly the number we got. All right, well, I hope you found this really valuable and let me know if you have any more questions. Bye.